Okay, in the previous video when we talked about the path difference and how it explained the interference pattern caused by two waves that interfere. Okay, so in this video we are going to go a little bit deeper, as in we're going to look at what are the factors that affect the way this pattern looks like. Okay, so remember earlier when we talk about the interference pattern, there are a few criteria, right? And then the first one, try to recall, the first one is the two source must be coherent. Okay, what is coherent means? They must have the same or consistent path difference. Alright, so in order to generate this interference pattern that is caused by two waves, you need two source. So if you use two source, right, let's say you are trying to use a light to generate a pattern. If you use two light bulb that is the same brand, the same brightness, everything the same, it looks the same, everything, the rating also the same, but you just couldn't get a nice or consistent path difference. Okay, so I mean, in conclusion is, if you use the same source of the wave, you cannot get a coherent wave. So this guy Thomas Young, he thought of a genius idea. He said that we just need one. Okay, we need one, and then in front of the one we put a single slit, so we limit it to a small hole there, and then it get diffracted. Okay, so when it get diffracted, it will spread out. So right in front of this small slit, we put a double slit. Okay, we put a double slit, and because of the spread out, right, so we can have the distance of that two slit a bit further from this single slit line. Okay, so that's the A and B here, the A and B. Okay, so they are a bit further apart from the single slit, and those waves, they will pass through A and B. So as they pass through A and B, right, what happened is the waves that emerge from A and B is exactly the same wave, as in their phase difference is going to be 0. Okay, so it's like you have one source suddenly become two source, and the two sources are exactly the same. Okay, that's the genius idea lah. So that's why the experiment also named after him is called the Young's double slit experiment. Okay, which is very important. Okay, in other part of the physics terms lah, huh? Okay, so on your same worksheet just now, where you draw where you trace the waves, so below that there's a diagram for you to draw this also. There's the Young double slit experiment. Okay, I want you to draw the semicircles here. Okay, so you need the compasses to draw that. That's better. Don't draw freehand. It takes some time, but you don't have to draw so many. Okay, but however, when you draw, right, I need you to extend these lines into a semicircle. So this diagram is not really very good, but that's the best I can find. Okay, so I need you to draw. So you draw at least 5. Okay, at least 5. I mean, 5 is good enough. 1, 2, 3, 4, 5. If you want to go to 6. Okay, so no need to follow this. This one is too many. Alright, so once you did that, then you can pause the video to draw first. So you will have something like this. But the one that I'm showing you here, I included the trough of this wave. Okay, just now are all the wavefronts. Wavefront, we always say that they are the peaks, right? So in this diagram here, I have the two sources just now, but I included a line in the middle of two solid line. So the solid line indicate the peak, okay, or the wavefront. So in between two solid line, I put the trough, the lowest point, okay, of the displacement. Okay, why I want to do that, of course, is to find the interference of constructive interference and destructive interference. Okay, so let's look at this point. So now we have these points here as I draw. That's where the two solids line intersect. Okay, which means that along this line, I'm going to get a constructive interference. Okay, so this is a line for constructive interference. I write somewhere here, constructive interference. And then I look for other points that have this trait. Okay, like this one here. So it's going to be like this. So if you draw properly, right, the line is going to be a bit curved. So this is also constructive interference. And then if I go to the other one below, then I have this constructive interference. All right, so now we look at somewhere in between. Somewhere in between, I use a different color. Cannot. Oh, cannot. It doesn't allow me to use a different color, but never mind. Okay, so somewhere in between, let's say this point here. You can see here, try to detect what I'm trying to draw. Okay, that's where the solid line intersect with a dotted line. You see that? Okay, solid line. If you draw freehand, it's going to be very messy. That's why I advise you to draw with compasses. Okay, so this is going to be the destructive interference. All right, and then we also have this. So it go exactly in between two constructive interference. So the pattern is going to go on to the side. Okay, I think we have seen this in the animation earlier when I talk about the superposition of two waves, right? The diffraction. Okay, so if this is light, then we cannot see all this kind of thing. If this is water waves, then we can see the region. So therefore, if it's light, then we put a board for it to get reflected in front, then we can see the colors. So that's drawing what I draw just now. So we get something like this. Okay, so there will be alternating bright, this is bright fringe, we call it fringe, the band we call it fringe, the bright fringe and the dark fringe. Okay, so it's dark, bright, that is going to be a pattern like this. Okay. Okay, so this is a nicer diagram now. All right, it's also showing you the zoom part of when they arrive at the plate there to let you see what is their phase difference. Okay, so the one that give you the bright light or bright band or bright fringe there, you can see that the two colors waves, it's not two colors but just to demonstrate that. So the two waves, they will actually like going in phase. Okay, phase difference is 0. Whereas if it is a dark fringe, it's going to be like this, which is the destructive interference there. Okay, so it's like a pi radian of the phase difference, so they always cancel off each other. Okay, so now come to an equation that governs this the phenomena, like I said just now, factors that will affect the way this pattern look like. X is the distance between two successive bright fringes. Okay, I'm trying to label here. Wait, let me label here. So that's X. Okay, so that's X also. Of course, in between two dark fringe is also X. Okay, but we just make reference to the bright one. So X is the distance between successive bright fringe, and lambda is the wavelength of the wave coming from the two slit here. That's the lambda, and they have lambda. All right. D is the perpendicular distance between these two slit, the double slit and the screen. And then we have the A is the distance between the center of these two slits. Okay, distance between the center of these two slits. So X is affected by lambda D over A. You have to remember this equation. X is equals to lambda D over A. Okay, so question is always more to comparison question. So they will ask you if the wavelength is the same, the A is the same, how X will change if the D is double. Okay, or they will tell you, oh, the second wave, there are 2 times of the wavelength, half the A. Okay, well, and then how the X will change. Okay, so which means that you just need this equation to work it out. Okay, comparison question mostly. Right, let's look at the next thing. Okay, because this one will lead to the next topic, so I just tell you this one first. All right, so we have the three one, you can see a 1 2 3 picture here. Okay, the first picture, let's look at the first picture, is real photo. It's formed by a real double slit. Width of each slit is fairly big, so that's the slit here on the top right here. Okay, it's a bit big, and then you will see this pattern here. Okay, so we have a bright and dark fringes, but it's like a bit blur. Okay, bright and then dark and then bright and then dark, but it's a bit blur. Okay, and then secondly is the ideal one. Okay, the most beautiful one, but it's the fake one. All right, usually the nice one is a fake one. Okay, it's not likely to happen, because in order to produce this, the slit width is going to be, I mean, it need to be very small. It need to be in the size of the wavelength of the light. Okay, which is very difficult to make. If you can make that, then you get this pattern. All right, so that's the very clear demonstration of the bright and dark fringes in between, and then it's equally bright in between there. Then the last one, this one is just for your knowledge. If you are using a single slit, we will get a diffraction earlier. When I started talking about the diffraction, right, I show a single slit. I say if the slit is small, and then the spread out should be bigger. If the slit is big, then it should just focus at the middle there. Okay, so later on we'll talk back about this. So let's move on first. Okay, so now we move on to some examples of the calculation questions. So first of all, we have the Young 2 slit. It has a wavelength of this, and then the slit are 40 mm apart. So that is the A there. That's basically the A. The distance to the screen D is, okay, they're already telling you 1.2. Find the separation. So x equals to lambda d over a. So you sub in 6.0 10 to the power of -7, then you multiply 1.20, and then you divide by the a in terms of meter. Then you should get the answer. Okay, very straightforward. Answer is this. And then we have the second one, also Young double slit, of course, because we are talking about this, right? The 10 bright fringe on either side is 3.44 cm. Okay, I mean, this between the center of this interference pattern and the 10 bright fringe. So from the center means this one here. So this is the center. So if you count 1 2 3 4 5 6 7 8 9 10, so that's the 10 away. That's equivalent to 3.44 cm. Okay, that's equivalent to 3.44 cm. So with this information, actually we can get the x. Okay, we can get the x. So we have the 0 to 10 is 3.44. Then you get the x. Okay, so x equals to lambda d over a. Alright, so a is what we need to find here. Wavelength is given, which is 5.9. So it's 5.9 -7 times 2.00 divided by a. Okay, so you should get this answer. 3.43 times 10 to the power -4. Alright, the rest of the question will be your assignment questions. I'll see you in the next video.